Hi. Okay, thanks for the introduction, James. Yeah, I'm Richard Keene. I'm a professor emeritus in atmospheric science at the University of Colorado. I arrived in Boulder as a student in 1968, graduated as faculty in 2011, and got my PhD in climate change, which is something a subject very few people actually have a PhD in, specifically climate change in the geography department. And most of my life experiences, my education, my jobs have been weather related. Climate researcher, astronomer. I've written books about weather, photographed clouds, and some of those pictures have appeared on US postage stamps. I love the mountains. That's why I live in Colorado, so I've climbed quite a few of them, done some glacier studies, chasing tornadoes, et cetera, et cetera, et cetera. Also, I am been observing the weather as a weather watcher since 1961, so I've lived through several climate cycles, which gives me some insights into here as to what I'm talking about, that I've directly observed that the cycles, weather goes up, weather goes down, you have droughts, you have wet periods, you have warming spells, you have cooling spells, you have years, lots of hurricanes, and other years, no hurricanes, but lots of snowstorms. And the place where a lot of this has occurred is Philadelphia. That's my hometown. There's two ways to study climate and many scientific questions. One is with models, the theoretical approach, where you take the basic physical equations and then work with those, and you can get some good insights. You can also take the empirical approach and get data. And as Yogi Berra would say, learn a lot by just watching. And that is my preferred mode. I've done the modeling, but I find it much more satisfying to get real live data and then extract whatever great truths I can from the data. Okay, I write books and, of course, about nothing else but weather, and there's some of the titles of them dealing with clouds and tornadoes, and even chapters on climate change in there. My PhD was about climate change in the Arctic regions of Canada, and there's a picture of my thesis, which became a minor publication, about 200 copies that were all bought up many, many moons ago, and next to my little Arctic dog here. Okay, when I wrote my PhD thesis, again, this is in the 1970s, I won't say consensus, but sort of the general feeling is that there's going to be any big changes in climate, it would be towards the cold side, with a new ice age being a very remote possibility, or a smaller ice age, or just a cooler period that we were entering upon. And there's the latest and greatest data as of when I wrote my thesis, an article by Budico and Asakura in the 1960s, and you can see from the 1930s to the 1960s, temperatures decreasing rather steadily, some ups and downs, but you can draw a trend line through it. And if you extrapolated that out a century or two, it was down at levels cold enough, several degrees colder than it is currently, that we could actually embark on a new ice age or a partial ice age with expanding glaciers, year-round ice cover at lower latitudes than we're having them now. So again, that was sort of the thrust of some of the research at that time, including mine, which the PhD thesis. And of course, back then, as now, there was speculation that the cause of this could be human, also that it could be natural. But in the human there, we had these cavemen shooting arrows into the upper atmosphere. They had very good bows and arrows with long range and affecting the stratosphere and affecting the climate. Okay, so here we are in Salt Lake City, Utah, 68th UN Civil Society Conference. And the slide says it's a rebuttal to the conclusions of the conference. And when I was invited to talk, it was advertised we'd be giving a rebuttal to the presentations at the conference. And I think, well, that's kind of interesting because it's at the very beginning of the conference, so I won't know what the conclusions are until the end of the conference. So how do I rebut these conclusions that are 2 days off? Well, the UN is very kind about that, because they actually determined the conclusions before the conference even began. That is the style of UN reports and UN meetings. They get these committees to work on something, but before the committee is selected to give a certain result. So they know what the result's going to be before they even start. So conclusions are predetermined and will be accepted. IPCC reports, the Intergovernmental Panel on Climate Change, is similar. The I, by the way, in intergovernmental, well, that's intergovernmental, it's not scientific. The UN is not a scientific organization. It does not produce scientific reports. It produces political reports. That's their nature, that's why they're here. I've been on the IPCC as an expert reviewer, did that a couple times before I got fed up with the process of spending much of my valuable time writing reviews, which were then ignored because they disagreed with this predetermined narrative. Here's the IPCC flowchart, and this is their version of the process that they use. Up there in the upper left, it says start here. Below that is the IPCC approves the outline. So the report is determined. The conclusions are determined right there at the first step in the production of this. The governments and government committees, the politicians, do their analysis, and then they start picking scientists that will fill in some numbers and give a bunch of pretty graphs to make it look like it's a scientific report. That's the blue at the bottom. And then at the end on the right there, it goes back up. And notice that the government committees are floating. They're at the top. And the scientific input is sinking to the bottom. There's analogies to that, but I won't get into that. But at the very end, what happens? More government review. So again, the results are predetermined. So knowing that, I can just read the UN documents describing what the conference is about, and I know what they're going to say, so then I can rebut it. So here it is, their outline narrative. Well, there you go. They tell you what the narrative is, and it's sort of summed up at the bottom there. We have less than 11 years. I don't know why 10. I don't know why not 12. But anyway, we have less than 11 years to avoid the worst impacts of climate change, and everything they do and everything they propose is based upon that conclusion. So that makes my job simpler. My job is to show that climate change, aka global warming, is not a problem, not a catastrophic problem, and does not deserve any massive intervention to keep these non-existent catastrophes from happening. Okay, more verbiage from the report. Okay, I'm going to start off with the thing I call my global warming quiz, so warm up your minds. Unfortunately, you're not here in the room with me, so I won't hear your responses, so I'll just give the answers to you. It's going to be a real easy quiz. It won't be graded. So, wacky weather. I have a list of 11 strange, abnormal weather events. So in your assessment, when did these events occur or will occur? And the selection there is A, before 1958, B, sometime after 1958 but before today, past 60 years, C, predicted by the IPCC to occur in the next 50 years, or D, it's so physically impossible, it's only in the movies or your wildest dreams. So these 11 events, I have Alaskan glaciers melt at the rate of 1 mile per year. That's pretty fast. You know, since most glaciers are 10 or 20 miles long, at that rate, it won't take long for them to go. Alaska bakes at a temperature of 100 degrees north of the Arctic Circle. So the century mark of temperatures ever go north of the Arctic Circle. North Dakota roasts, which is a little more severe than baking, at 120 degrees. Hurricane hits Boston with 180 mile per hour winds, which is Category 5 strength winds up north in Boston. A hurricane kills half of the population of a large city. A hurricane hits San Diego, a place known for its peaceful and boring climate. Half a dozen hurricanes hit the east coast of the U.S. A dozen tornadoes strike Los Angeles. A major U.S. city is hit by a hurricane, tornado, and earthquake in the same year. Just think what that would do to insurance rates. The U.S., the warmest year ever. 20 states set, it's almost half of them. There's 50 states. 20 set new all-time heat records. And then the last one, I'm venturing out to Greenland, which is not part of the U.S. unless Mr. Trump closes his deal and does buy it. Greenland warms, and out there in Greenland, they're raising crops like barley and making their own beer, which is a sign of a civilization on Greenland. So I'll let you mull it over for 10 seconds, and I won't await your reply because I can't hear you. But here we go. So there you go. I hope most of you got this right, but I have no way of knowing. 10 out of 11 really did occur, and before 1958. And this list here, if there's specifics like a town or a year, it's listed there. Like Charleston, South Carolina, hurricane, tornado, and an earthquake in 1886. Not too bad. Hurricane kills half the population of a large southern city, Galveston, Texas, one of the wealthiest cities in the South on the Gulf of Mexico. Half the population were gone. The town was devastated, but they recovered. They built a seawall. Another hurricane came in 15 years later, and they went through that one pretty fine. So they did adapt to severe weather events and learn from the past. Okay, so there's the list. A dozen tornadoes struck Los Angeles in 1983. Happened to be, and that was in one day, and that was during an El Nino. And that's actually one of the side effects of El Nino, are a lot of storms at low latitudes in the U.S. crossing Southern California, New Mexico, Texas, Florida, and the Gulf Coast. And that's what happened in Los Angeles. And yes, indeed, 1,000 years ago, Vikings moved to Greenland, and they grew their own barley to make beer. They make beer now, by the way, in Greenland. They advertise it, but they have to import the barley from Denmark. So Greenland is still not as warm as it was 1,000 years ago because they cannot make truly indigenous beer now. Here's the 6 hurricanes striking North Carolina and the East Coast in 2 years. Excuse me. Okay, another question. Who was the first president or presidential wannabe? Because one of these guys, you may guess, did not make it as president. But which one of these 5 was the first one to talk fairly substantially about climate warming? You have choice of Jefferson, McKinley, Kennedy, Carter, and Al Gore. Well, keep guessing. Here you go. This guy. Yes, Thomas Jefferson. Al Gore wishes and acts like he was the first one, but actually it was Thomas Jefferson, who was our 3rd president. And he kept the log of the weather every day for 50 years. Here's a report from July 1776 in Philadelphia. I think you all have some idea what he was doing in his trip to Philadelphia. But notice down there on July 4th at 1 p.m., So if anyone ever asks you what did Thomas Jefferson do at 1 p.m. on July 4, 1776, well, he may have been writing and signing documents of some sort. However, at 1 p.m., he went outside with a thermometer and read the temperature. Good for him. Okay, so there we go, Thomas Jefferson. And what else did he have to say? A change in our climate. This is in one of his publications, his book, Notes on the State of Virginia. A change in our climate is taking place very sensibly. Heats and colds are becoming more moderate. All things pointing to a more moderate climate, milder winters, and snows are less frequent and less deep. What Jefferson was seeing was the end of an event called the Little Ice Age, which was from the 1400s through the 1600s. Among other things, it froze the Vikings out of Greenland, so they stayed there and just stopped reproducing and stopped populating their villages, and the population just withered away, and they stopped making beer. That would be in the 1400s. That cooling spell moderated and got warmer at the end of the 1600s into the 1700s, and that's what Mr. Jefferson was noting. Other people noted the same thing. President of the Royal Society a few years later writes this about reduced ice in the Arctic. You can sail farther north, seeing the same event. Noah Webster also noting that, well, indeed, I know not whether any person in this age has ever questioned the fact. So in other words, Webster seemed to think there was a consensus going on, which is another parallel with today. And U.S. Weather Bureau noted similar thing. Farther on, this is 1922, climate had been warming for 200 years, and they're taking note of it. So, temperatures and the global climate seem to have moderated over a 200-year period, then cooled off, and now they're moderating again slightly. Well, what about side effects of this? The charismatic megafauna, as biologists like to call it, otherwise known as polar bears because they're cute, they're cuddly, they're warm, but can they swim? So are polar bears drowning because the ice in the Arctic is a little thinner some years than other years? Well, no. You may have occasional polar bears that didn't have swimming lessons and get washed up on the beach, that happens. But globally, this is the count of polar bears all across the Arctic from the 1980s or 1960s through the 2000s, 40 years. And notice from the 1960s up until the 1980s, the populations increased. Maybe it's real, maybe it's that more people are up there counting them. But anyway, since the 1980s, populations have been pretty stable at about 25,000 polar bears in the Arctic. I imagine the count of people is a little bit less. So polar bear populations in the entire Arctic are stable. Some places, some areas are having a few more, and in some of those places they're becoming a problem, raiding garbage cans and breaking into houses and stealing silverware and so on. So the natives, the locals in these places actually want to get hunting permits to thin them out a little. And other populations of polar bears are decreasing a bit. So people are noting that and saying they need protection. So depends where you are, but overall, polar bear populations are not changing very much. And polar bears, as true to their name, they like to swim. Ursus maritimus, they call them, the sea bear. That's the Latin name for polar bear. So melting ice is no problem, they can swim. And here's some polar bears having a beach party. They're cooking a penguin, and I know people always jump on me and say, no penguins in the northern hemisphere, no polar bears in the southern hemisphere. So you got it all wrong. But they're underestimating the global economy. Those penguins are actually imported from Antarctica. Okay, what about hurricanes? Well, okay, first of all, I'll point out that this diagram from Mr. Gore's movie has the hurricane spinning the wrong way, unless you're in the southern hemisphere. So maybe he's painting pandering to the Australian and Chilean audience. But we'll let that go by. But sorry, hurricanes are decreasing. This is a chart showing the number of hurricanes of various intensities striking the land of the U.S. Why did I use this statistic? Well, it's a very robust statistic, as scientists like to say. If a hurricane hits the mainland of the U.S., it is noticed. And that's been true for 200 years, so it's a good long record. And it doesn't matter if it hits Florida, hits Long Island, hits Galveston, Texas, it's reported. Somebody knows about it. So it's a very, very good data set. And you can see since the 1940s, the past 70 years, the number's steadily decreasing. And for all hurricanes, for the strongest ones and for the not quite so strong hurricanes, all showing this general downward trend since the 1930s and 1940s, which, by the way, globally was a fairly warm period. Off of China in the Pacific, same thing. Tropical storms and hurricanes, they call them typhoons over there, decreasing since the 1950s. So 60 years decreasing in the Pacific Basin, hurricanes, typhoons off of the coast of China. What about tornadoes? Decreasing. Overall, actually over the period of time for this whole graph, you can see there's that major bump in the middle, which is dominated by 1 year, 1974. But you can see definitely since the 70s, the number of strong to violent tornadoes is decreasing in the U.S. Well, what about small tornadoes, little ones? Well, those numbers are increasing, and there's a very simple reason for that. In the 1970s, we had this new phenomenon called storm chasers, of which I was one, going out looking for these things. And they would find them, and they would find small ones. But if it was a tornado, they would call them in. My first tornado was a tornado that only I saw. If I hadn't seen it and hadn't called it in, it would not be in the record. So the small tornadoes numbers are increasing, but that's an observational effect. Again, people are looking for them. The big ones, though, the ones that take out neighborhoods and kill quite a few people, those ones are decreasing. Okay, what about sea levels? And we have this famous event, can this guy lower the seas? Like he promised at a speech he had in Denver. You might remember this at the presidential convention. They had these pseudo-Greek styrofoam columns. It was really kind of a beautiful, setup, classic setup. And Mr. Obama was saying, I'm certain that generations from now, we will be able to look back and tell our children that this was the moment when the rise of the oceans began to slow and our planet began to heal. That's impressive. So, did it work? Did he lower the seas? Well, fortunately, he's late to the show because this guy already did. That's Mr. Bush. So there's a bit of facetiousness going on here, but at least Mr. Bush never claimed he was going to. But this graph does show the essential fact that sea levels are rising steadily at the minuscule rate of 2 or 3 millimeters a year. Well, 2 or 3 millimeters a year is about, I'll do some quick arithmetic, about a foot in a century. If you can't outrun a foot in a century, you got other problems. So, it's not a catastrophic sea level rise. And it's been rising at this rate ever since people have been measuring sea levels, which goes back in some places in Europe, for example, back to the 1400s and 1500s. Very slow, stately rise. And why is it rising? Well, it's from the end of the Ice Age. And ice was still melting up until a few centuries ago, up in the high Arctic from the Ice Age, which was 10,000 years ago. And also the oceans are warming since, 18,000 years ago. A lot of the Northern Ocean was ice, and the ocean when temperature is near freezing all the way to the bottom. And the ocean is still warming up since the past few thousand years ago. So that's what's showing on this graph. What Mr. Bush is pointing at there is really just a glitch. It was dropping for a few years, but subsequent data has sea levels rising again at 2 or 3 millimeters a year like it has been always doing. And the little bumps you see along the way are mostly due to El Nino, which is a warming of the Pacific Ocean, which is the world's largest ocean. So when the Pacific warms and the sea levels rise temporarily for a year or two in the Pacific, the global average also responds. So what you're seeing here is a steady increase over centuries, punctuated by little spikes due to El Nino, from which invariably the sea level then comes back down. Well, what about climate models? They don't lie, do they? This is one way to study a phenomenon, is to get basic physics, put it into a computer, pick the proper equations, and calculate what temperatures on Earth should do. And there's some of these equations, there's some of the data. Lower right shows the carbon dioxide increasing, and it is increasing. So if we put CO2 into the atmosphere, how much will the Earth warm? Well, let's do a mind experiment. For every 10,000 air molecules, mostly nitrogen and oxygen, if we add 1 CO2 molecule, which is equivalent to what humans have done over the past century, 1 CO2 molecule per 10,000 molecules of air, how much does this CO2 warm the atmosphere? Well, back up a little. How and why should CO2 warm the atmosphere? Well, it's pretty simple. Carbon dioxide is a greenhouse gas. It absorbs infrared. So in a nutshell, sunlight comes down, heats the ground. The ground gets warm, radiates infrared radiation up into the atmosphere. Carbon dioxide absorbs some of this radiation. The carbon dioxide warms up and then re-radiates some of this heat energy, this infrared radiation, back down to the ground. So now you have more radiation coming back down to the ground, sort of reflected, but not quite. It's re-radiated back down, and the ground heats up a little more. And that would be that 0.2 degrees. I will point out that there are other greenhouse gases in the atmosphere. The biggest one is water vapor, H2O, which is at least 30 times more abundant than carbon dioxide and has a much bigger greenhouse effect. And it's about a 33 degrees Celsius or 50 degree Fahrenheit, 60 degrees Fahrenheit warming of the Earth due to this greenhouse gas of water vapor. Well, it's a good thing that occurs. Don't get it in your mind that the greenhouse effect and climate warming due to greenhouse effects is bad, because if we did not have this water vapor and CO2 in the atmosphere, we would not have this 60 degree warming. The Earth's average temperature would be about 0 degrees Fahrenheit, at which case there would not be much life left on Earth. There'd be no plants growing anywhere, no plants for the animals to eat, and therefore no animals. Basically, the Earth would be lifeless, like, say, one of the moons of Jupiter or a place like Pluto. It'd be a frozen world. Okay, so it's not just CO2, though, that can cause warming. You have these feedback effects, that complicate the situation. Sunlight comes down, it's absorbed by the ground, it's absorbed by air molecules, the CO2 in the air. Clouds, it reflects off of clouds, it reflects off of oceans, it reflects off of ice. It does all sorts of things. The sunlight, it doesn't all just go down to heat the surface of the Earth. And the heat radiation, the infrared radiation going back up, doesn't all get absorbed by carbon dioxide. Some of that gets absorbed by clouds, gets reflected back down. Some of it, most of it, goes back into outer space. So again, it's a very complex situation. And if here's an even more complete version of it with all these loops, how one thing leads to another, leads to another, leads to another. And these things are called feedbacks. And so the climate modelers, the theoreticians, have a lot of liberty at judging how big these feedbacks are. So if infrared radiation is absorbed by water vapor and then goes back down to the ground, heats the oceans, how much water evaporates from the ocean? Well, you can make up a number or try and measure it. You have a lot of degrees of freedom to tune your model to fit the data, or at least come up with a larger greenhouse effect and make it look like it's bigger than it is. To most people, the models are like this proverbial elephant from Indian legend, I believe it is, where if you close your eyes and you touch the elephant, it could be a rope, it could be a piece of leather, it could be a sword, whatever, depending on what part of the elephant. You got to be careful there. But some, people look at climate models. Some say, well, it's mostly volcanoes because that's the only thing I understand. Some think, it's clouds reflecting, or ice, or carbon dioxide, or methane, or oceans, or water vapor, you name it. So there's many pieces of this puzzle, and very few, if any, people have a full grasp of all of them. Even more people know nothing about the climate models, and to them they're just black boxes where they have a forcing input data. They put something into the model, like say the sun has a big flare and so much energy comes down. Well, let's throw it in a climate model and see what comes out, without having any understanding what the model is, and they don't really care. They say, well, then the model produces such and such, produces, a tornado in Singapore or something like that. Okay, well, better luck to them. But nobody really understands the models, and nobody really understands the many ways they can produce erroneous results, the problems with the models, the failings, the lackings, the stuff that isn't in there that should be. And it shows when you compare the model outputs with the data. This chart shows the output of about 100 models, different models, running independently, starting in 1982 and then running forwards to the year 2028. Interesting thing about starting in the past and running to the future, you can compare the past to observed data to see how well it's doing, and running it into the future, it gives you kind of a prediction as to what the future may bring. Well, these 102 models disagree quite widely with each other. You can look at the end, the total warming is anywhere from half a degree up to almost 2 degrees. Down there at the bottom where you see the little blue dots, that's data. I'll show next slide is going to be more clear on the data. But notice the heavy black line with the big dots on it. That is the average of these 102 models. So let's compare the average of 102 models programmed by the best and brightest theoreticians on the planet and compare it to the data. Well, whoops, not too good. The average is well over 1 degree Celsius of warming by the end of the century. By 2020, what year is that? 2025. Well, the observations indicate a fraction of that kind of warming. Instead of a degree, it's more like 1 or 2/10 of a degree of actual warming observed over the past 40 years. And this is based on the best global temperature measurements, which are not weather stations irregularly scattered around the planet, irregularly scattered in time. Stations open, stations close, they go defunct. But satellite observations, polar orbiting, orbits over every square inch of the Earth's surface, looks down, measures the heat radiation coming from the ground, and therefore measuring the temperature of the ground of the Earth and the lower atmosphere, and also weather balloons, which have the advantage of not measuring the temperature on a runway by a big asphalt tarmac or on a city street or on a piece of ice or something like that. It's actually measuring the temperature of the atmosphere over thousands of feet of air above all these things, which eliminates the local effects and the fairly large local effects of, say, a big asphalt tarmac, a square mile of black asphalt at an airport. So, the models are wrong by, let's say, a factor of 5 times too big. They do get some things right, though. So, here we have the same slide again with one thing added. I'll get to that in a second. But notice that the 102 models, the average, shows that steady warming going on, although far too rapidly. But there's 2 bumps, dips in the early period in the 1980s and the 1990s. Well, those are due to volcanoes. 2 big volcanoes on planet Earth in that period. Volcano in Mexico called El Chichon in 1982, and one in the Philippines, Pinatubo, 1991. What volcanoes do is, yes, they spew some greenhouse gases, water vapor, carbon dioxide, but that's not the big thing for climate. What they also send out is sulfur dioxide, gets up into the stratosphere. We're talking 10, 15, 20 miles up. SO2, sulfur dioxide, joins with water vapor to make little droplets of sulfuric acid that sit up there for months or even years as kind of a haze layer, which dims the sunlight coming back down to Earth. So it dims, reduces the amount of solar energy reaching the ground, thereby cooling the surface of the Earth by some fraction of a degree. And the models, strangely, do catch this process fairly well. You can see the dips are about the same size as the observed, but it's superimposed on a global warming signal, which is far, far too big. Well, the black, gray dotted line is a simple model that I wrote myself and ran on a TI-57 calculator and scratch pad back of an envelope. There's not much in it. There's greenhouse gas and volcanoes. And I did some empirical estimates of how much these greenhouse gases and volcanoes would affect the climate, and it fits the observed pattern pretty well. You can see the dip for El Chichon, the dip for Pinatubo, and the overall increase over 40 years is in that 0.1 degree range that is observed. So this model does reproduce, and it's simpler. It doesn't have all those feedback loops, the spaghetti that you saw in some of those previous diagrams. All it has is CO2, the direct effect, the radiation effect of CO2 radiating infrared back to the ground. That's where that story ends. And volcanoes dimming the sunlight reaching the ground, and that's it. No more to that model than those, but it really fits the observations better than many of these multi-million-dollar computer-run extravaganzas. So what does that mean for the future? Well, the simple model, if you extrapolate another 70, 80 years to the year 2100, it would, quote, predict or project, as they like to say, a warming of about 0.3 of a degree. You know, 1/4 of a degree. That's Celsius, more like 1/2 degree Fahrenheit. The IPCC conglomeration of models goes for at least 2 degrees of warming, or if you prefer Fahrenheit, 3 or 4 degrees. Well, 3 or 4 degrees is substantial. It could have some economic effects, but 1/4 of a degree is not. So some other hard facts that come from this preceding analysis. Since 1979, there's been warming, 0.3 of a degree, but half of it can be blamed on the fact that the volcanoes cooled off the first 20 years, which leave the second 20 years relatively warmer. So the absence of volcanoes in the past 20 years and the clear atmosphere letting more sunlight in has contributed to half of that warming. A little less than half is due to greenhouse gases. And after you subtract those two out, there's just some bumps up and down left. And what are those? It's our old friend El Nino. Most of those bumps can be attributed to El Nino, which is a temporary thing, 1 or 2 years, warms up for a year or so, then cools back down. Warms up, cools back down. So El Nino does not have a climate effect, it's short-term weather effect, but the volcanoes and the CO2 do have a climate effect, but it's almost infinitely small, a few tenths of a degree. What else? Okay, the IPCC models exaggerate the warming by factors, depending on the model, of at least 2 up to about 10 times what is actually observed. Which means, not to worry, 100 years from now, our grandchildren will be measuring temperatures and enjoying a climate very much like it is now. In the absence of a massive volcano or an asteroid impact, climate will probably be undetectably different than now. I would challenge you to go out and measure with any common thermometer a temperature change of 0.3 of a degree. It's beyond the accuracy of a thermometer, so it's not measurable. Enjoy the relatively mild climate we're having now between ice ages while it lasts, and please, please, pretty please, produce enough carbon dioxide to feed a tree. They appreciate it. Thank you.